In this course, we're going to learn about coordination compound, coordination chemistry. What is coordination chemistry? Coordination chemistry involves the reaction between ligands and metals. So this will form a metal complex. And the strength of the metal to ligand bond is determined by whether the ligand is a strong ligand or a weak ligand. In this course, we will also learn about the electron arrangement in the d orbital. So in school, we are taught that when you have a d orbital, okay, so there are five types of orbital, right? Let me erase this. Let's draw a better one. So there are five orbitals. Okay, there are five orbitals. So we can actually draw them like this. Okay, this is what you will learn in school. Okay, so the level here looks the same. They are degenerate. Okay, the energy is degenerate, means the energy is the same level. So when filling up the electrons, we always fill in as single electrons first in all orbitals, followed by completing the orbitals. Okay, that's how you fill in the electrons, right? Now, in this course, we are going to look at the energy between these five, right? So these will actually be splitted into two different energies, okay? Where the lower energy here, the one with 3 orbitals is known as T2G, while the level having 2 orbitals is known as EG. Okay, so this is the arrangement of the d orbitals in an octahedral system. When we discuss about the peculiarity of a coordination compound or organometallic compounds, we no longer discuss using this. We are going to use this. Okay, so we are going to look at the splitting energy between the EG level and the T2G level. Okay, so this is what we are going to look at. And we're also going to be we are going to look at the the name of d orbitals. Okay, the d orbitals, there are 5 d orbitals, right? So the name is d xy, we have d xz, we have d y z. We also have d z square, and there's also d x square minus y square. Okay, so all the squares will be the EG level. Okay, so these two will be grouped as EG, and the other 3 here, they will be categorized under T2G. Okay, so you see, this is how the d orbitals are splitted. Okay, when ligands coordinate to the metal, the differences in splitting energy is determined by whether the ligand is strong or a weak field ligand. We're going to look at that in this course. It is very important to know how to write the electronic configurations of all these elements, especially the transition metals, because the transition metals and most of the p block elements and also some s block elements, when these elements are going down the group, then the atomic number is getting greater, bigger, and this will increase the number of n. The n will increase greater than 3, 4, 5. Okay, so there will be a lot of sub-levels involved, and there is also a scenario where some of these electronic configuration will not obey or disobey the Aufbau principle. So technically, the writing of the electronic configuration will follow the Aufbau principle. So it will follow the Aufbau principle. Okay, so this. So according to Aufbau principle, electronic configuration will always be written from the lowest energy level to the highest. So we always start with 1s, 1s2, because maximum number of electrons occupying the s orbital is 2. So 1s2, 2s2, 2p6, 3s2, 3p6, and so on. So these are the examples of configurations, okay, considering the 4s and 3d orbitals and 4b. So the electronic configuration before 4s is actually the same. And because we are actually focusing on the d orbital, we only focus on 4s and 3d. Because the changes in the electronic configuration will occur in 4s and 3d orbitals, and those in the square elements in the square indicates anomaly, which means these elements, their electronic configuration disobeys the Aufbau principle. We shall look at that later. And this diagram right here is actually showing you the level of n, the energy level n equals to 1 until n equals to 2, 3, 4, 5, 6, and so on. So when n equals to 1, there's only one orbital, 1s. When n equals to 2, there will be 2, s and p. When n equals to 3, there are s, p, and d. And when n equals to 4, there's p, s, p, d, and f. So the increment in the number of n will add to the type of orbital. So when n equals to 4, a new orbital comes in, 4f. Okay. If you look at this diagram, the arrangement of the energy level when the 4s and 3d, when the 3d orbital is empty, okay, when it's empty, the 4s energy level goes down, even though 4 n equals to 4 is higher in energy compared to n equals to 3, but when the number of n increases, the arrangement in the energy level fluctuates. That depends on the whether the filling up of electrons in these orbitals will stabilize which energy level. So 4s is lower in energy compared to 3d, okay, when your 3d is empty. Okay, so that is why when arranging electrons, we always write the electron arrangement starting from 1s, okay, and then 2s, and then 2p. So this will be like 6 electrons, okay, and then 3s, 3p, after filling up the 3p level, we don't actually go to 3d, okay, so we go to 4s. So 4s is the lower energy compared to 3d, and then only filling up the 3d orbital. Okay, so if you look at the Aufbau principle, the outbound diagram. We start with 1s, okay, 1s, and then 2s, just like this diagram, and then followed by 2p, okay, and then 3s, okay, we follow the diagram. After 3s is 3p, and then 4s, okay. That is why this is how the outbound diagram is generated. Okay, the diagonal arrow actually indicates the position of the energy level of every sub-level. Okay, yeah. So when your 3D orbitals are filled with electrons, this will actually lower down the energy of 3D. So 4s now has become higher in energy. When 3D is empty, 3D has a higher energy compared to 4s. So 4s is lower. Okay, that's why we fill in the 4s first. But when your 3D is filled with electrons, and so does your 4s, this will reduce the energy level of 3D. Okay, so now 4s has become higher in energy. That is why the losing of electrons is always starting from losing electrons from the 4s orbitals.
Let's look, for example, some elements that you want to write the electronic configuration. So, for example, the element is the chromium. The atomic number of chromium is 24. Okay, 24. So basically, when you look at the periodic table, the D block section, chromium is located in the fourth column. Okay, so the first column will be scandium, and then followed by titanium, vanadium, and chromium. So usually the number of electrons occupying an orbital will assign the location of the element in the periodic table. However, there are some elements that do not obey this system. There are some elements that disobeys the Aufbau principle. According to the Aufbau principle, we have to fill in the 4s first and then followed by the 3d. So the 4s electrons will be filled with 2 electrons, will be filled first, then followed by the 3d orbitals. So looking at the atomic number of chromium, the 3d orbital will be occupying only 4 electrons. Let's revise this again. We know that 4s has 1 room. The d orbital will have 5 rooms. Okay, so the d orbital have 5 sublevel, 5 rooms. So every room will be filled with maximum number of 2 electrons. So when filling in the 4s first, we need to fill in the 2 electrons first in 4s and followed by the other 4 in 3d. This is what obeys the Aufbau principle. However, there are some reasons why some electronic configuration disobeys Aufbau principle. If you draw the electronic configuration by following the Aufbau principle, this will be the way. However, this is not right. Why? the best electronic configuration will consider the stability of the electron arrangement. What do we mean by that is an orbital that has a fully filled electrons or half filled. So a d orbital has 5 rooms. A fully filled d orbital will have 10 electrons, 2 electrons in each room. A half-filled d orbital will have half from 10 electrons. That will be 5 electrons. So 1 electron occupying each room. So this will lead to the stability of the electronic configuration. Now looking at this example here, the electron arrangement according to Aufbau principle is correct. However, it's not stable. Why? Because there's still 1 room left to be filled so that the electron configuration will achieve stability by making sure that this d orbital is half filled. Remember, fully filled or half-filled orbitals will lead to a stable electronic configuration. Now, because of that, we need to add another electron here. Now, we don't actually add from another chromium atom or another element. That electron will come from 4s. So this electron from 4s will be transferred here, making the new configuration this. Okay, it will make the new configuration that. So instead of writing 4s2 3d4, we actually write 4s1 3d5. So this is wrong, this is correct. All right, so these are the cases for anomaly. Now, usually for elements having atomic number greater than 20, some of these elements, not all of them, some of these elements that has atomic number more or greater than 20 will experience anomaly, which means if you have written the electronic configuration of this element by following the Aufbau principle, due to some reason, if you see the d orbital can be converted to a better stability, if there is an opportunity, if there is a room for adding another electron to achieve a greater stability, so the electronic configuration for that particular element will now disobey the Aufbau principle. Because according to Aufbau principle, we always fill in the low energy level first, making sure that low energy level is fully filled first, then followed by the higher energy. So if we follow the Aufbau principle, okay, definitely the 4s will be fully filled first, because in an empty orbital, in an empty 3d orbital, 4s is the lowest energy compared to 3d. So of course your 4s will be filled by 2 electrons first. After that, the following electrons will be occupying the 3d. So that will give a 4s2 3d4 for chromium. But because there is another room that when we add another electron, it will make the 3d orbital half filled. So one electron from 4s is transferred to the 3d and making the electronic configuration 4s1 3d5. Now, 4s1 3d5 is not the full electronic configuration. What I'm showing you here is the important part that is affected, okay? The rest of the electronic configuration before 4s will remain the same.
There are two types of ligands, donor ligands and acceptor ligands. So let's go back to basic. Now we have an atom, okay? So that's the nucleus, right? And in the nucleus, there's a neutron and protons. And what is going around the nucleus is their electrons, okay? Electrons. Now, in chemical reactions, electrons are the important particles taking part in attacking the electrophilic center and donating electrons, accepting electrons. These are all the job of an electron. The neutrons and protons do nothing, all right? So we are actually looking at the behavior of electrons. When an electron is lost, the element becomes positively charged. It becomes a cation. If an element accepts electrons or gain electrons, it becomes an ion or negatively charged. The negatively charged species is also a nucleophile. And the species that's poor in electron, these are the electrophiles. So we are actually talking about electrons. Now, when forming a coordination bond, a bond between a metal and a ligand, a covalent bond between a metal and a ligand, that is a dative bond. A dative bond or a coordination bond is actually developed, established when a ligand donates or contributes its electron to the metal. So in this case here, the ligand is donating electrons. So the ligand is an electron donor. Being an electron donor, there are two categories of electron donor, the sigma donor and the pi donor. So please remember, these ligands donate electrons, never the protons or neutrons, it's just electrons. So when there's a ligand, then let me draw some example. For example, this is a ligand, L. Now, generally, L will represent a ligand. When the ligand has a lone pair or one electron, a lone pair means two electrons, but there are also ligands that contributes just one electrons. So when the ligand contributes its electrons to the metal, the ligand is actually contributing the electron to the metal and placing it in the d orbital of the metal. So the metal is actually receiving electrons from the ligand. The metal is accepting electrons from the ligand. Okay. So that electron will be placed in the orbital. But which orbital? When the metal accepts electron from the ligand, this electron will be placed in the d orbital of the metal. Remember, the covalent bond is not about electron is lost and makes the species, the original species becomes cation. A covalent bond is actually an overlapping of orbitals. So the orbital containing that electron, when overlaps with another orbital, that is how the electron is passed on to the other species. So that overlapping will form a bond, whether it's a sigma bond or a pi bond. So if the electron is actually occupying, if let's say this lone pair on the ligand is occupying the s orbital of the ligand, that will create a sigma bond. But if that electron is coming from the p orbital of the ligand, it will actually create a pi bond. Anyway, whatever bond it is, in a dative bond formation, in a coordination compound, when the ligand contributes its electron to the metal, it will form a sigma bond. Okay? The ligand contributes electron to the metal, it will form a sigma bond. If there is another extra of lone pair occupying the pi orbital of the ligand, and that also is donated to the metal, that will create a pi bond. So what is a sigma donor ligand and a pi donor ligand? A sigma donor ligand is when the ligand donates a pair of its electrons to the empty metal orbital. So a pair of electrons in the ligand sigma orbital is donated to an empty metal orbital. So for example, we have the ammonia. Okay. We also have the phosphine. Okay. These are the example of a sigma donor. Because the nitrogen here and phosphorus here, they have a lone pair. This is the only lone pair that they have, that when it's donated to the metal, it makes a sigma bond. The pi donor ligand, for example, the fluoride, chloride, hydroxide, water, the electrons that are donated to the metal, the lone pair will still form a sigma bond. So let's say you have a fluoride. Okay, you have a fluoride. When its electron is donated to the metal, it will form a sigma bond. Okay, it will form a sigma bond. But because this fluoride have additional lone pairs of electrons occupying the p orbitals, that also could be contributed to the metal empty orbital. And because that additional lone pair is occupying the p orbitals, and if that electron is going to be contributed to the empty metal d orbital, definitely there will be overlapping of orbital between the p orbital of the fluoride and the d orbital of the metal. And this will create a pi bonding interaction. The ligand can also become an acceptor, electron acceptor. Now, this is what you should understand, the basic of accepting and donating electrons. The donating of electrons will happen when that donor is rich in electrons or have extra electrons, have lone pairs, negatively charged, okay? Whereas a species that accepts electron, they are electron poor species. They are usually the positively charged. If they are metal ion, they are high oxidation state metal ion. What else? They don't really have a lot of electrons to be donated. So the concept of donating electrons and accepting electrons depends on whether that species has a lot of electrons or less electrons. It's not always the metal will become the electron acceptor, and it is not always the non-metal, the ligands will become the electron donor. So please recall Lewis acid and Lewis base concept. The Lewis acid and Lewis base defines an acid. An acid is something, a species that accepts electrons. So it doesn't matter whether that species is a metal or a non-metal. If it has the potential towards accepting electrons, and that is because that species itself is having low number of electrons. So it will be acidic. It will be known as a Lewis acid. Acidic, okay? Something that is acidic will accept electrons. Something that is basic will give out electrons. So the species that has higher number of electrons will be able to contribute, to give out, to donate electrons to other species that's poor in electrons. So those species having a high number of electrons, being able to be a donor of electrons, they are basic. The term basic here means because they have a lot of electrons. So they tend to give out. They don't accept because they already have a lot. So they can donate. It's just like, imagine you are rich, super rich, and there's no reason for you to not give or donate your money. But if you're not rich and you have no money, you have least amount of money, you tend to accept money from others. So you are acidic. So accepting electrons is acidic. Giving out electrons is basic. So this is not restricted only to metals or non-metals. Any elements, any ions, any species that accepts electrons are Lewis acidic, whereby if they donate electron, they are Lewis base, they are basic. Okay, all right, please remember that. Now, the ligand, apart from being a donor, a sigma donor or a pi donor, it can also be an acceptor. Accept what? Accept electrons. We are talking about donating electrons and accepting electrons. So, in order for a ligand to become a donor, whether a sigma donor, okay, whether a sigma donor or a pi donor, okay, sigma donor and a pi donor, that ligand will need to be highly capable of giving electrons. So that ligand is basic. Okay, that ligand has higher number of electrons. And for a ligand to become an acceptor, the ligand itself has to be not preferring to donate electrons because the ligand has low number of electrons. Now, what actually makes the ligand has low number of electrons? You see, the example given here is carbon monoxide and cyanide. Let's look at carbon monoxide. Okay, so this is carbon monoxide. Carbon monoxide is a gas. Okay, it's a C triple bond O. It's a gas. Now what happened? The electronegativity difference between carbon and oxygen is large. It makes the oxygen here more polarized and it makes the carbon more electropositive. So the electron polarization is moving towards oxygen greater because the electronegativity effect of oxygen is greater than carbon. So that creates a huge difference in electronegativity value between carbon and oxygen. So electron will be moving towards oxygen. And because the electron density is pushed, the electron density is pushed towards oxygen. Okay, electron here is moving towards oxygen. When electron density is moving towards oxygen, it makes the electron density on carbon lower. When it makes the electron density on carbon, okay, the electron density on carbon becomes lower. and this makes the carbon acidic. And because of that, this carbon here can be a pi acceptor ligand. Now, why is it called a pi acceptor? Now, what I actually explained a few minutes ago is the characteristic of an acceptor. What makes it a pi acceptor? Okay, so let's look at the formation of a metal complex. For example, let's say we want to react a metal ion, okay, with a carbon monoxide, right? So we know that carbon monoxide will contribute its electron to the metal. Carbon monoxide contributes 2 electrons to the metal. And this contribution makes a bond between carbon and the metal. And that bond is called a sigma bond. Okay? Whenever there's electron involved, okay, in joining two elements, they will form a bond. This is a sigma bond. Now, this carbon here is acidic due to polarization of electron towards oxygen. Metal, when we talk about metal, we talk about transition metal, yeah? Transition metal, some of them have very, very low number of electrons in their d orbital. Some of them have quite a few, okay, in the d orbital. Some have higher number of electrons in their d orbital. So remember, these 2 electrons that is contributed by the carbon in carbon monoxide to the metal is going to be placed in the d orbital of the metal. The d orbital of that metal is already having its own electrons. By accepting 2 electrons from carbon monoxide, this will add electron to the d orbital of that metal, which will result in the increment in electron density in the d orbital. When that happens, electrons will repel each other. There will be a greater electron-electron repulsion. Although initially, there are a few electrons already occupying the d orbital of the metal before carbon actually donates its electron. That electron-electron repulsion is already there. However, by accepting another 2 electrons from the carbon will add more to the electron-electron repulsion. So electron-electron repulsion is going to be greater due to the contribution of electrons by carbon. In this example, the carbon is from carbon monoxide. So that electron will repel. The repulsion is so great that it has to move out. The electron has to move out. The electron has to go somewhere to reduce the electron-electron repulsion. But where would the electron go? The electron will be returned to the carbon, not to the oxygen, because the contribution initially came from the carbon. So due to a greater electron-electron repulsion in the d orbital of the metal, that electron in the d orbital metal, the metal d orbital, is given back to the carbon. Now, when electron is given to an element, it will have to be placed in the orbital. The electron cannot just float anywhere. So, if you remember the atomic orbital diagram, okay, or the molecular orbital diagram, we know that the lower energy is sigma, followed by pi. Then you have the non-bonding, okay. Then you have the pi star, and then the sigma star, right? Okay. These are the bonding state. So the lowest energy is the sigma state, then followed by the pi, and the non-bonding, and this one here is the anti-bonding state. So occupying the anti-bonding state is not that stable, okay? Unless the bonding and non-bonding state is already fully occupied, then electrons will occupy the anti-bonding state. Electrons will not occupy the anti-bonding state first because it is the highest energy. Now, electrons from the metal d orbital will be transferred to the carbon. Now, the carbon bonding and non-bonding is already occupied. What is left is the pi star and sigma star state, energy state. This electron that's coming from the metal d orbital cannot occupy the bonding or non-bonding anymore. They have no choice. So they have to go to occupying the anti-bonding state. Between the sigma star and the pi star state, the pi star is the lower energy state among the anti-bonding energy state, okay? So this electron will be occupying the pi star state. It will go here. So that's the name here, pi acceptor, okay? The carbon is actually accepting electron from the metal d orbital and putting, okay, putting that electron on its pi star state, the carbon's pi star state. This action of giving back electrons by metal to the carbon is called pi back bonding. It is called pi back bonding. Okay, it's a back bonding. All right. Ligands, when coordinate to metal, will form metal complex. So let's revise. Ligand coordinates to metal. Ligand contributes its electron to metal. These will result in the formation of a metal complex. So what is a metal complex? A metal complex is a compound where a metal is covalently bonded with a ligand. So an example of metal complex, okay, there are many examples. For example, we have ferrum coordinating to carbon monoxide, 6 carbon monoxide, right? So 6 carbon monoxide or other ligands, okay? We can have chlorine, okay? Then we have, let's say, water, okay? Or another CO, right? Okay, so this is a metal complex. So these are known as ligands, okay? So these are ligands. So what are ligands? Ligands are compounds or atoms, okay, molecules that form a dative bond with a metal. So the whole molecular structure is a metal complex. Okay, and the metal center can be any kind of metal of any oxidation state, right? So that's an example of a metal complex. Now, you see, in this example, iron is coordinated to carbon monoxide through carbon. Iron is coordinated to chlorine and water. When iron is coordinated to water, it coordinates through oxygen. All right? Okay. So these ligands, okay, all these ligands, chlorine, carbon monoxide, water, they are called terminal ligand. Why? Because this ligand coordinates to only one metal. Okay, terminal ligand. Now, what if the same ligand coordinates to another metal? Okay, what if the ligand coordinates to another metal? All right, so let's look at some examples. We have iron, okay, iron, CO, then we have L, okay, iron, L, so we have another CO, okay, and the same thing here, right? Okay, so these carbon monoxide are terminal ligand. Why? Because the carbon monoxide is coordinating only to one metal. But this chlorine is now a bridging ligand because the chlorine now is holding two metals. Now, for a bridging ligand, the number of metal coordinating to that particular ligand can be more than two. Okay, when there is a bridge actually holds two things. Okay, so in this example, two metals. It can actually coordinate to more than two metals. Okay, so if the ligand coordinates to only one metal, it is called a terminal ligand. So this kind of ligand is called, okay, this kind of ligand is called a bridging ligand. Okay, a bridging ligand. So a bridging ligand is not only chlorine. This is only as an example. It can be carbon monoxide, it can be amine, it can be sulfur, okay, it can be water, okay, it can be anything. All right, so this is a bridging ligand. So in a nomenclature, how do you identify if the molecule is containing a bridging ligand? So usually when we name a compound, for example, we name it as ethylene diimine. Okay, so when you name it as ethylene diimine, we know that the structure will be, if it's ethylene diimine, okay, so this is the structure. Okay, there is no bridging. Okay, this is the structure. But if there is a bridging ligand exist in the molecular structure, the name will contains mu. Mu indicate bridging. Okay, so mu dash what. Okay, so when you see a mu, so that is a bridging. That is a bridge. Okay, so here because the bridge is formed between the metal and chlorine. So chlorine is the bridge. Okay, so it's a mu chloro. Okay, mu chloro. If it's a fluorine, it's a mu fluoro. So mu dash the name of the bridge. Okay, the name of the bridge. Okay, right. So that is bridging ligand. What about ligands from the hydrocarbon group? Okay, from the hydrocarbon group. Now, in metal complexes, there are two types of metal complexes. We have the coordination compounds and also the organometallic. Okay, so you see, if we draw, if the structure is this, okay, if this is the structure, right? This is a metal complex that is also known as organometallic. Why is it called organometallic? Organometallic are metal complexes, but the metal complex is formed between a metal and a ligand where the coordination occurs through the carbon. So if you look at this structure, okay, if you look at this structure, the iron, the metal, it can be any metal and any ligand, okay? The metal coordinates to chlorine, 4 chlorine, and 2 carbon monoxide. And the coordination with carbon monoxide occurs between iron and carbon, okay? So because of this, the complex is known as organometal. This is an organoferrum. Organoferrum. Okay, organometal is a general name for it. So if it contains iron, so this is an iron or organoferrum. If the metal center is a ruthenium, then it's an organoruthenium. If the metal center is an osmium, so it's organoosmium. Okay. Now, the number of ligand where metal coordinates to the carbon, it has to be at least 1. So here, the complex contains 2 ligands where the iron coordinates to the ligand through carbon. What if the complex, okay, what if the complex contains, okay, this is carbon monoxide. Okay, let me draw it again. Okay, what if the complex is, okay, this complex, is this an organometal, organoiron? Yes. Why it is an organoiron or organoferrum? Because there is an iron or metal carbon bond. At least there must be one ligand in that molecule that form a coordination bond with the metal through the carbon atom. Okay? But if let's say we have this, okay? Okay, let's say we have this. Is this organometal or organoiron? No. This is just a coordination compound because in this structure, okay, in this structure, there is no iron to carbon. There's only iron to nitrogen, iron to oxygen, iron with chlorine. Okay, there is no bond that forms between metal and carbon. Okay, so all of these examples are metal complexes. They are metal complexes. Okay, all of these are metal complexes. how we differentiate, we distinguish organometal from other metal complexes is when you see the metal forms a coordination bond with the ligand through the carbon. Okay, so uh, that's the difference. But all of these are metal complexes. Okay, so these ligand, okay, is called a chelate, a chelating agent. A chelating agent. It forms a chelate with the metal. Now, why is it called a chelate? You see, the ligand is not just like carbon monoxide, where coordination happens between the metal with just one atom in the ligand. Okay, so in this example, the green structure, in this example, all these ligands are monodentate. They are monodentate. Okay, they are called monodentate because the ligand coordinates to the metal through one atom. Okay, like chlorine, carbon monoxide, all right? The same goes for this structure. Okay, there are 4 monodentate ligands, 3 chlorines to 1 carbon monoxide. However, this is a chelating agent because the metal coordinates with one ligand through 2 atoms. Okay, the chelation site is 2. There are 2 chelation sites. Okay, where iron coordinates to both atoms of the same ligand. So this is called a bidentate. Dentate here is derived from denticity. Denticity means how many coordination sites. Okay, the number of coordination sites. So for a monodentate, okay, for a monodentate ligand, the coordination site is only 1. So it is called a monodentate. But for ligand like ethylene diimine, okay, ethylene diimine, this, okay, what do you call this? Ethylene diimine. This is actually derived from glycol. Okay, this is a glycol. Okay, so that one ligand has 2 coordination sites, and both coordination sites, both oxygen and both nitrogen, coordinates to the iron, to the metal. So those kind of ligand are known as a bidentate ligand. Okay,